Hi guys, welcome to my YouTube channel. Today we discuss the adjoint of matrix, and yesterday we have discussed about the minor and cofactor of determinant, how to find the determinant and expresses the minor and determinant, and today uh, we discuss the adjoint of uh, adjoint of matrix, and uh, how to find the inverse of matrix here. uh, Hi guys, before starting you guys to channel, subscribe to my channel, and second things, uh, sure you video watching completely uh, completely to my channel and share it with the friend, and like hit button. So here I discuss the adjoint of matrix. I want to say a few something word education need need very change to life, and and education education is a very important in life, every time, every day, everywhere. And important topic, adjoint of square matrix. uh, how to express the adjoint of matrix. let let A is equal to Aij be any matrix, where A is a square matrix, and we know that square matrix have row and column are same. Then the matrix called the square matrix, uh, and we get the other matrix, B, then find the inverse of A matrix, and let B is equal to any matrix. We consider the any matrix B is equal to Ai J, where I J is the cofactor of the element. And yesterday we have to go to the start minor and cofactor, and how to find the minor and cofactor. Minor, any take any element and passes through the ith row and jth column, then the we call the minor of determinant. And minor is multiplied by minus power of I plus sum of I plus j of -1. Then we call the cofactor of determinant, and help to us the minor and cofactor to make the adjoint. And here we discuss the adjoint of matrix. To find the adjoint of matrix, the Aij is the cofactor of determinant. The transpose B here, listen, be carefully. Transpose B means that row change in column and column change in the row. Then we call transpose of matrix B called the adjoint of, and it is Cofactor is denoted by Aij, and minor is denoted by Mij, and the value of Mij is multiplied by sum of row and column of -1 is called the cofactor. So here we discuss the adjoint of matrix, and how find the adjoint of matrix. Adjoint of matrix, let A is equal to Aij be a square matrix. So we consider the square matrix A11, A12, A3, A21, A22, A3, A31, A32, A33. Here same rows, same column, and 3 by 3 order this matrix. And how to find the adjoint? Adjoint of A is equal to transpose of B, then call the adjoint of matrix. We see carefully. Adjoint of A. Find the adjoint of A, and definition of adjoint of A. The adjoint of A is equal to transpose of A11, A12, A13, A21, A33, A23, A31, A32, A33, where A11 is the cofactor of first row and first column, first row and second column, first row and third column. So where we know that Aij is denoted by cofactor is denoted by Aij, then cofactor, the new matrix B, the transpose of B. Here first row change in first column, and second row change in second column, and third row change in second column. So this is a new matrix, and we find the new matrix. We have a new matrix, and next step, find the inverse of A, and how to find the inverse of A. And usually inverse of A, and tell about the inverse of A. Next topic, and look here, inverse या reciprocal of square matrix. Inverse या reciprocal, just opposite word, inverse या reciprocal of a square matrix. So define the square matrix, and how to inverse in this term. Let A be a square matrix of order n. Let A be a square matrix order n, then a matrix B is called the inverse of A. If AB is equal to BA is equal to IN, and I have read about the AB is equal to BA is equal to IN, and we know that on the theorem AB is equal to BA is equal to identity. And next previous video we discussed the AB is equal to BA is equal to IN, and here then we can say that inverse of the square matrix A is denoted by A inverse, and find the value of A inverse. And how to find the value of A inverse, and can we express as A inverse? Look here, very important theorem for 12th, and this theorem applied to any matrix and find the inverse. The, I can read about this theorem. The inverse of a square matrix exists if and only if A is a non-singular matrix. I repeat that here. This theorem call the inverse of a square matrix exist if and only if A is a non-singular matrix. Here create two conditions: sufficient condition and necessary condition, and any take the necessary condition and we get the sufficient condition, then theorem is proved. And take before if part, let A be a non-singular matrix of order n, and here we know that a singular matrix. Yesterday previous video we discussed the singular non-singular matrix, where any matrix and determinant are does not zero, then matrix called the singular matrix, and then determinant of A does not there and denoted by determinant A does not zero. So we know that adjoint of A is equal to adjoint of A is equal to determinant of A product identity. And previous theorem, if a square matrix and order n, then we proved that A product A adjoint of A is equal to adjoint product of A is equal to determinant product of identity. We can see here both are equal. They are equal each other. Then we apply the three terms, one by determinant of A, and here we see the one by determinant A, product A is equal A product adjoint of A is equal to 1 over determinant of A product adjoint of A product A is equal to identity, because determinant of A over determinant of A, then cancel determinant of A over determinant of A, those are cancel. Then this term is neglected, and other step of and look here, let B is equal to adjoint of A by determinant of A. Let B is equal to whole term, and we know that A is equal to A is equal to IN, where B is the inverse of A, A is the inverse of A. So that hence B, that is adjoint of A over determinant of A, is the inverse of matrix of any inverse of matrix, which is the inverse of matrix by definition of inverse, any definition of inverse. And other part we take the inverse of matrix A, then we find the A is a non-singular matrix. only if part only any uh, second term we bring the second term and let A be a square matrix of order n. Let inverse of A exist. Let B be the inverse of A. Let B be the inverse of A. And then by definition of inverse, if AB is equal to identity, AB is equal to identity implies that the determinant of product of AB is equal to determinant of identity is equal to identity. And next term, look here, product of AB is equal to identity. Product of AB is equal to identity implies that determinant of product of AB is equal to identity. Is equal to identity implies that product of identity A and identity B is equal to 1. The determinant of A does not zero because product AB product determinant of AB product determinant of B is non-zero, and we reach the determinant of A product determinant of B is non-zero, hence A is non-singular. And we important notation noted that, and we to write the note on the your notebook note copy, and very important notation here, write and transpose inverse of A is equal to adjoint of A over determinant of A. This gives a formula for finding inverse. Here finding inverse, then A inverse is equal to adjoint of A over determinant of A. And second notation, A product inverse of A is equal to A inverse product A is equal to identity. And we take any example tomorrow, and we show that A product inverse of A is equal to inverse of A, the product A is equal to identity. And next note, inverse of A inverse of A is equal to A matrix, and other inverse of product of A dot product of B is equal to inverse of B product inverse of A. And tomorrow we take very important matrix, and this method apply in this matrix. And I want to say some word. We know I speak every time, every day. Good pen, good teacher, and good book can change life. And mathematics is the most beautiful subject and most powerful creation of the human spirit. And I hope all students have to understood in this topic, and you find the inverse of any matrix, adjoint of any matrix, and minor and cofactor of determinant any matrix. You know that I hope you enjoyed it, and I shall see you again. Come back watching this video. Thank you so much. Thank so much. watching this video. Thank you so much.